Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome to the Deep Dive. Today we're focusing on a piece of technology that really forms the backbone of modern scalable networks, the Virtual Local Area Network, or VLAN.
It really is. It's this core concept that's just, absolutely central to how big organizations manage both their efficiency and their security.
Right. And if you need to get up to speed on network segmentation and fast, this is where you start. We've gone through a whole stack of sources on this, covering, well, everything.
Everything from the basic definition to the real nitty-gritty of how they're deployed and, importantly, the security trade-offs you have to make.
So our mission today is pretty straightforward. We want to give you that shortcut to understanding the mechanics, the security side, and the practical uses of VLANs so you can walk away and apply this knowledge. Let's jump in.
So let's start at the very beginning. When we say VLAN, what are we fundamentally talking about?
Okay, so at its core, a VLAN is a custom network that you create from one or more physical networks, or LANs.
It lets you take devices that could be scattered all over the place, different floors, different buildings even, and group them together as if they were all plugged into the same box. It's one logical network.
And this whole idea, the shift from physical to logical, it came about to solve a really critical problem with old school networks, right?
Yeah.
The whole broadcast domain issue.
Exactly. I mean, picture a totally flat network, just one big LAN. When any single computer sends out a broadcast message, which they have to do for things like ARP, that message hits every single device on the whole network.
Every server, every printer, every laptop.
Every single one. And each of those devices has to stop what it's doing, process that incoming packet, and figure out if it's relevant.
Which most of the time it isn't.
Right. It's just noise. And that noise creates this huge CPU overhead. It slows everything down. And it's a security nightmare because everyone's in the same big open room.
VLANs basically build walls in that room.
They do. They stop that inefficiency cold. And here's the aha moment for you. Once you put interfaces into separate VLANs, host A can shout as loud as it wants.
But only the other hosts in its own VLAN will hear it.
Precisely. Everyone in VLAN 20 is completely oblivious to the broadcast storm happening over in VLAN 10. It is software-defined isolation.
Okay, so let's get into the plumbing here. If all these devices are physically plugged into the same switch, how does the switch know which packets belong to which group?
It all comes down to a simple ID number. Each VLAN is identified by a unique number, a VLAN ID.
And there's a specific range for those.
Yep, the standard range is 1 to 4094. As the administrator, you just go in and assign a VLAN number to each port on the switch. From that point on, the switch's internal logic only allows data to be sent between ports that have the exact same number.
So each VLAN becomes its own little isolated island, its own broadcast domain?
Exactly.
But that works for one switch. Most networks are, much bigger than that. What if I have my accounting team on VLAN 10 on a switch on the first floor, and more accounting folks on VLAN 10 on the third floor? How do they talk?
And that is where the concept of trunking becomes absolutely essential. You can't scale without it.
Okay, so what is a trunk?
You basically designate one specific port on each switch to be a trunk link and run a single cable between them. But this link is special. It's configured to carry the traffic for multiple VLANs at the same time.
So it's like a multi-lane highway for all the different VLANs running over one physical cable. But how does switch B know which car or packet belongs in which lane?
This is the really clever part. It's a process called 802.1Q tagging.
802.1Q. Got it.
When a frame is heading out of switch A across that trunk link, the switch actually modifies it. It inserts a tiny 4-byte digital tag into the frame's header.
And that tag contains the VLAN ID number.
Exactly. The frame zips across the cable, hits switch B, and the first thing switch B does is look at that tag. It says, this is for VLAN 10, removes the tag, and then forwards the clean frame only to the ports that belong to VLAN 10.
That's incredibly elegant. So the physical location of the user becomes completely irrelevant?
Totally irrelevant. You're grouping users by their role, their department, their function.
Yeah.
Not by what wall jack they're plugged into.
And from an operations standpoint, that must be a huge time saver. Someone from sales moves to a new desk.
It's just a simple software change.
Yeah.
You reassign their new port to the sales VLAN. No recabling, no changing IP addresses. It's all just configuration.
And let's bring it back to security. What's the immediate payoff of all this segmentation?
Well, the payoff is that you shrink your attack surface. By breaking up that one giant broadcast domain into dozens of smaller ones, you inherently limit how far a threat can travel.
So if the HR department's server gets compromised,
The damage is contained. That threat is, in theory, stuck inside the HR VLAN. It can't easily see or reach the finance department's servers because they're on a totally separate logical network. It is, foundational network security.
okay, let's dig into those VLAN IDs a bit more. You said 1 to 4094, but the sources we looked at show it's not quite a free-for-all. There's a structure to it.
Oh yeah, there are definitely rules. It's fascinating, actually. For starters, VLAN 0 and the very last one, 4095, are reserved. You can't touch them, can't use them.
And then there's VLAN 1.
Right. VLAN 1 is the default. Every switch out of the box has all its ports in VLAN 1. It's always there. You can't delete it, but you can, and many do, use it.
So the real day-to-day working range is a bit smaller.
It is. The normal range, where you'll do most of your work, is VLAN 2 up to 1001. That's where you have full control, create, edit, delete, whatever you need.
But then it gets weird again, right? With some legacy stuff baked in.
It does. You hit VLANs 1002 through 1005, and those are often hard-coded by manufacturers like Cisco for really old network types, things like Token Ring and FDDI.
FDDI, Fiber Distributed Data Interface. I haven't heard that in a while.
Exactly. You probably won't use them, but you also can't delete them. They're just there. After that, you get into the extended range, 1006, all the way to 4094, which is really for huge enterprise environments that need thousands of segments.
And to really understand why trunking is so critical for that scale, the sources had a great example. They sort of painted a picture of what happens if you don't use trunking.
Yeah, you run out of ports almost immediately. Think about it. If you have, say, 24 different VLANs that need to communicate between two switches.
Without a trunk, you'd need a dedicated cable for each one.
24 separate cables. If you're using a 48-port switch, you just used up half your ports just connecting to the other switch. There's almost no room left for actual computers or servers.
Whereas a single trunk link using 802.1q tagging does the job with just one port on each end.
It's the only way to scale. And the performance gain is massive. By killing all that broadcast traffic, you slash network congestion. Each VLAN really does act like its own private LAN.
So a workstation can use the full bandwidth of its port without having to compete with traffic from a totally different department.
It leads directly to lower latency, fewer data collisions, just a better experience for the user all around. You're trading a tiny bit of processing power for the tagging, but you're getting huge gains in efficiency.
So we've established why you'd use them, but it sounds like there are a few different ways to actually implement them to assign devices to a VLAN.
Right, there are a few models, and you choose based on what you're trying to achieve. The simplest and by far the most common is the port-based VLAN.
Sometimes called a static VLAN.
Exactly. It's just what it sounds like. You, the admin, go into the switch and manually say, port 5 is in VLAN 10, port 6 is in VLAN 20.
The advantage there is that it's simple, it's predictable, you know exactly what's happening.
Very predictable.
Yeah.
The switch knows a frame's VLAN membership the second it arrives, just based on the physical port it came in on. The downside, though, is that it's rigid. A user moves their desk, you have to manually reconfigure the port every single time.
Okay, so that's the static approach. What if you need something more dynamic?
Well, there's a more niche model called the protocol-based VLAN.
And that's not based on the port, but on what's inside the packet.
Precisely. It looks at the layer 3 protocol. Is this an IPv4 packet? Is it an old IPX packet? And it assigns the VLAN based on that protocol type.
That seems very specific. When would that be useful?
It was mainly for older environments that were running a mix of different network protocols all at once. In today's world, where just about everything is IP, it's not really practical. There's no need to segment by protocol if it's all the same.
Which brings us to the third type, which feels like the most powerful for a modern mobile workforce, the MAC-based VLAN.
Oh, absolutely. This is the game changer for mobility. With this model, the VLAN assignment is tied to the device's unique hardware address, its MAC address.
So it doesn't matter where you plug in. The network knows who you are by your device's fingerprint.
That's a great way to put it. You have to create a central table, basically a database, that maps specific MAC addresses to specific VLAN IDs.
So a doctor's tablet can be plugged into a port in the ER or a port in their office, and it will automatically get placed on the secure medical device's VLAN every time.
Every single time. It's incredibly powerful for that kind of environment. The setup is more complex. You have to maintain that big mapping table. But the operational payoff, eliminating all that manual port configuration, is enormous.
Okay, to really drive this home, let's do a quick-fire comparison. The big practical differences between a classic flat LAN and a modern segmented VLAN setup.
Sure. Let's start with performance. On a flat LAN, latency is generally high because every broadcast hits every device.
Right. With a VLAN, much lower latency and much higher performance.
Exactly. Then there's cost. To segment a LAN physically, you might need more switches, more cables. It costs more.
A VLAN uses the hardware you already have, so the cost is way less.
And then the most fundamental difference is just packet handling. A LAN is a free-for-all. It advertises packets everywhere. A VLAN is targeted. Packets only go where they belong within that specific domain.
The sources also mention some protocol differences, like LANs using older tech like Token Ring, while VLANs use management protocols like VTP.
Yeah, VTP, the VLAN trunking protocol, is a good example of the operational advantage. It's a tool that lets you make a VLAN change on one main switch, and it automatically pushes that change out to all the other switches in the network.
So you don't have to log into 20 different switches to make one change.
Right. It saves time and prevents a lot of human error.
So if we summarize the big advantages, you reduce the size of your broadcast domains, you can group users by function instead of location, you enhance security. It seems like a no-brainer.
It is, for the most part. But, and this is a really important but, moving all this control from physical cables into software introduces its own set of risks and vulnerabilities.
Okay, so what are the specific dangers we're creating with these virtual walls?
Well, the biggest one is that the walls aren't perfect. A misconfiguration can cause a packet to leak from one VLAN to another. But the more malicious threat is something called VLAN hopping.
That sounds like exactly what you're trying to prevent. How does that work?
An attacker can craft a special packet with two 802.1Q tags on it, a double tag.
Okay.
The first switch sees the outer tag, which looks legitimate, strips it off, and forwards the packet. But now the inner malicious tag is exposed, and the next switch in line reads that tag and sends the packet into a restricted VLAN it was never supposed to reach.
Wow. So the segmentation itself becomes the vector of attack.
It can be. And you also have to remember, if a virus gets onto one machine, it can still spread like wildfire through the entire VLAN that machine is in. The segmentation only contains it to that one logical group.
And there's another limitation, right? A VLAN, by design, can't talk to another VLAN.
Correct. By default, they are completely isolated. If someone in accounting on VLAN 10 needs to access a server in finance on VLAN 20, you need a layer 3 device, a router or layer 3 switch, to act as the traffic cop between them.
Which adds another layer of hardware and complexity to manage.
It does, especially in very large networks.
So given that complexity, what's the tipping point? When should an organization definitely be looking at implementing VLANs?
The general guidelines are pretty clear. Once a single LAN gets to be over, say, 200 devices, it's probably time. Or if you're just seeing a ton of broadcast traffic bogging things down.
Or if you have a specific group like executives or R&D that handles sensitive data and needs that extra layer of isolation.
Exactly. Or, at the simplest level, if you just want one physical switch to act like it's 5 separate, smaller switches.
We've covered a ton of ground here. It's clear that VLANs are this foundational tool for building efficient, scalable networks. They let you manage traffic and boost security by creating these logical groups that completely ignore physical location.
They absolutely solve that huge problem of the flat, noisy, insecure broadcast domain. But as we've seen, there is a trade-off. When you move that network boundary from a physical cable into software code, you create new, complex vulnerabilities like VLAN hopping. And you create the need for routers to handle all the communication between those VLANs.
Which brings us to our final thought for you to take away from this deep dive.
Given that VLANs are really a necessity for any network of scale, and knowing that they bring these unique software-based risks with them. How much extra management overhead should an organization be willing to accept to fight those risks? We're talking about things like implementing extra firewalls, complex intrusion detection systems, dedicated routers all to mitigate the vulnerabilities that come with the flexibility. It's this constant, complicated balancing act between logical power and real-world security.
Thank you for joining us for the deep dive. We'll see you next time.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.
CTSS